Dean Academic for UG courses at NIT Durgapur. He is the project leader of Green Steel from NIT Durgapur under the Indian Australian Mineral Scholar Network program of Government of India and Australia. He had worked in various reputed iron and steel industries like Tata Metal Links, Sri Metal Link, and KIC Metal Links, and served as the junior engineer to assistant manager level from August 2000 to July 2009. He joined in Department of Metallurgical Engineering at IIT BHU, Varanasi as a senior technical officer and completed his PhD degree from the same institute in 2017. Dr. Mandal has published 45 plus journal articles, one book chapter in reputed peer-reviewed international journal, book and conference proceedings. He has two granted patents in the field of steel making and waste utilization. He is a regular reviewer of various journals like Metallurgical Transaction B, JOM, Journal of Sustainable Metallurgy, Waste Management and Research Plasma, Science and Technology, Mineral Processing and Extractive Metallurgy Review, Journal of Cleaner Production, etc. He is also handling several projects and consultancy projects from SERB, Government of India and Industry. His present research interests include green steel making, agglomeration, DRI, smelting reduction, plasma technology for metallurgical use, and metallurgical waste recycling. Dr. Mandal is recipient of Outstanding Scientist Award by ISRO and Venus International Foundation in 2018, and the Best Employee for contributing company-wide initiative awarded by Tata Group in the year 2007. He is life member of IIM, IIME, MGMI, ISTE, and member of IE. He is also acting as a Indian Council member of IIM Kolkata and the Executive Committee member of Division of IEI. With this small introduction, now I welcome Professor Arup Kumar Mandal to this last session to deliver a talk on the topic, a new concept of environmental friendly, sustainable, single step impurity removal process from liquid iron. So it's over to you, sir, now.
Yeah, thank you, Gauraji. Actually, I'm sorry for some technical delays due to my laptop problem. Okay, I think my PPTs are visible to all.
Yes, they are visible.
Okay. And I am audible also?
Yes, sir, you are audible.
So before going to the presentation, a very short brief of our NIT Durgapur. It was established in 1960 as a RE college, you know, and up to 2023-4, it was affiliated by the University of Burdwan. 2003 onwards, it is transformed to NIT as a central funded technical institution. 2007 onwards, so NIT Act is declared, and 2009 we received the NIT statute, and we are an autonomous institute by MOE, Government of India, like NIT Rourkela. This is our ranking NRF details in last 21, 22, and 23. We have engineering, science, as well as the management department and humanities also. We offer undergraduate, postgraduate, doctoral, as well as the postdoctoral receipt. These are the courses we generally offer. This is for the intake, and this is our institute profiles. In our department, we have process and extractive metallurgy, which I involved in this group. Along with this, we have environmental degradation of materials department area, research area, physical metallurgy area, advanced materials, modeling and simulation area. These are our faculty details. So my topic is a new concept for environment-friendly, sustainable one-step impurities removal process of liquid iron by hydrogen plasma. I will discuss. Actually, this is a new concept. As we are talking about the green steel, people are generally talking about the use of hydrogen. As you know, the first session, it was by Professor Gigi Roy, Reve sir. They briefly discussed regarding that. Before going to my presentation, my view of green steel making and in which area we incline to do the research. My aim, main, if you ask me regarding the green steel, obviously it is the environment friendly process for using the producing the steel. But we have to consider why we will choose the green steel. As said in first session, nicely discussed regarding the less CO2 emission. Not only the CO2 emission, actually to minimize the carbon footprint, uh, to reduce the air pollution, we have to think about the climate change effect so that we can promote the development as a sustainable manner. Okay. Then people are working in this direction towards the carbon neutrality for a greener future. So obviously, the green steel should produce with as it should produce with the lower emission. It should also produce by using the lower energy also. Means the energy utilization should be lower also. Third, major points we have to consider like the byproduct generation. We have to consider the process which we develop, it should generate less byproducts. Okay, and the developed process should be higher efficiency also. So first one is the measure to CO2 emission. This is one data. Generally, the fossil fuels is mainly the culprit for producing the CO2. If you see the statistics, 2022, you can see we produce near about 60 billion ton CO2 from the fossil fuels and industry. This is very important. So it means the fossil fuel, not only from the steel industry, also from the power generation unit also. Like if you see 75 to 80% power is generated through the thermal power plant in India. Therefore, simultaneously, to make the greener environment, we have to think about the greener energy source, not only the greener steel production, also to produce the energy in a greener manner, because as India, like country, as I discussed, the fossil fuel based thermal power plant industry. So in case of iron and steel making, if we want to decarbonize iron and steel industry, uh, so our aim will be obviously to reduce the emission. So what are the general pathways generally we are following is, one, it may be like the carbon capture. Why we are talking about this carbon capture? Because our target to steel production is 300 million tons by 2030. So it means we cannot, and our target to net zero is by 2070. Therefore, stepwise manner, we have decided to cut down the CO2 emission. So first one is which we have decided like uh, to reduce the CO2 emission in different process. Okay, so as we cannot replace 100% blast furnace in today's scenario, then what to do? We have to run this blast furnace. Therefore, as we add the we will add the CO2 in this process, then the suitable carbon capture is one process which we can decrease the CO2 emission. It means carbon capturing NCC and its utilization is a burning topic nowadays. People are thinking so that instead of producing the green hydrogen, if you can produce the brown hydrogen also, so you can uh, mm, decrease the CO2 emission, or you can take care of the environmental consideration. Okay. So another thing is to more efficient technologies adaptation. Like if the energy, your technologies is less energy intensive, then obviously you indirectly decrease the CO2 emission. As the I discussed, energy is highly related to CO2 emission. And finally, we can think about like the carbon-free fuels uses as and reductant. Like it may be some biomass, or it may be uh, hydrogen. Okay, as we discussed, the blast furnace we cannot ignore nowadays. As 94% of iron making, if you see, the worldwide produces through this blast furnace route. And the energy requirement to produce the steel is near about 18.8 gigajoule per ton. And where we produce 1.85, or sometimes it is called as near about 2 ton of CO2 equivalent per ton of steel productions. So as we know, this redox reaction is the responsible for this CO2 emission, as we conventionally use the fossil fuel as a reductant. Okay, so uh, if you see the benefits of this carbon as a reductant, so it is cost effective. Obviously, it is cheaper raw materials as compared to the any other raw materials, means as a reductant. So, and versatility of use, different forms you can use to produce the metals. It may be as a pig iron, is hot metals, as well as in the form of DRI. In these different types of product you can produce by carbon. Scalability is also advantage for using the carbon for steel making. And also, if you consider the sustainability point of view, if you use the biochar as a renewable source instead of biofuels, then it will be advantageous. But the disadvantage is mainly if you consider the environmental impact, which I had discussed, limited availability of the raw materials, because this is the fossil fuel having a limited stock. Okay, this is not the renewable energy sources. This is this is actually the disadvantages. And the product which is generated in the form of toxic chemicals, CO2, sometimes as it contains sulfur also, fuels contain sulfur also, therefore it also generates the SOx. Then SOx as well as the CO2, both are the health hazardous waste. It generated in the form of slag and as due to the silica content of this iron is high. So what are the challenges of this uh, carbon use as a reductant? Is quality of the iron, because carbon efficiency is there. Carbon dioxide emissions is the major one, which I have discussed. Control of the process, like if you vary the temperature, pressure, or amount of carbon used, can affect the quality of the final product. It absorbs the some amount of carbon, which is required to decarbonize again for in a second stage, like the steel making or primary steel making, or in the secondary steel making process. Or the challenges is which I have already discussed, negative environmental impact, uh, like SOx generation. So alternate iron ore reduction is which is coming into picture, or people are working. Some pilot scale projects are also going on to use the hydrogen as a replacement of the carbon monoxide. If we consider as a reductant, how hydrogen will be advantageous, or uh, uh, what are their disadvantages? So advantages is the source of hydrogen is plenty, like water is the source of from where you can generate the hydrogen. So in case of hydrogen as a reductant, first benefit will be the less carbon emission. Hydrogen has a high energy content, and can be produced from the renewable sources, then the energy efficiency will be higher. Any type of iron ore you can produce for, you can use to reduce, like in the form of fines. If you want to reduce, hydrogen can reduce. In the form of lamp also, hydrogen can reduce. Okay. But I will. There is some challenges in flexibility of iron in conventional DR route. I will discuss. Cost saving is also advantageous if you think a long term basis, because this process is more energy efficient, and price of hydrogen in future it will decrease, because nowadays it is very costlier one, but gradually it will decrease. Therefore, in for the long run, it will give the cost saving. But the major disadvantage is present condition. It is like the cost and availability of hydrogen to generate the hydrogen in a greener way. This is another disadvantages. And hydrogen embrittlement of the iron, it is another problem, because like hydrogen can diffuse in the iron lattice and it can weaken the materials. Ultimately, it will be the reason for hydrogen embrittlement. Another technical challenges like the precise control of the temperature, pressure, and other parameters. And as hydrogen is explosive in nature, so handling is also a problem. And if the hydrogen is produced from fossil fuel, then it is the disadvantage. If you it will affect the environment. If you produce the hydrogen in a cleaner way from the um, uh, uh, water splitting method, then it will give the less environmental impacts. But if you want to produce the hydrogen from the conventionally fossil fuel, then it will affect the environment. So challenges is nowadays obviously the cost one. Cost is the higher, and development of efficient technology to for this reduction process. Formation of this water vapor, it can also reduce the yield of this desired product. And as I discussed, this is the challenge, how to safely use the hydrogen as it is the flammable gas. If we compare the reduction by carbon and hydrogen, in case of reduction with the carbon, the byproduct is CO2. But in case of reduction with the hydrogen, the byproduct is H2. So uh, as fossil fuel is used, therefore it is the lower cost. And as still now the hydrogen generation is costlier, therefore the reduction with the hydrogen to make the iron, it is high cost. So environment impact wise, obviously it is higher for carbon and it is lower for the uh, hydrogen. And less pure iron is produced as the carbon is diffuse. And in case of hydrogen, the purity of hydrogen you can get high. So in which area we can introduce hydrogen, or we can replace the conventional fuel. So if you see iron making process, if you think about the BOF steel making, in integrated steel plant route, the iron making area, only hydrogen can be replaced up to 10%. It means that 10% conventional fuels can be replaced by the hydrogen area. Therefore, this integrated steel plant would having less uh, probability to use hydrogen. Okay. If you go for the smelting reduction route, you can replace up to the 30% of this hydrogen. But there is a probability for using replacement of the conventional fuel by hydrogen up to 100% if you go for the DRI route, direct reduced iron route. Therefore, major research which is going on, if you see, it is the hydrogen-based DRI process. Okay. So hydrogen-based different DRI routes like hydrogen DRI melted by electric arc furnace. It means iron ore, it will be reduced, directly reduced using the hydrogen to make the HDRI, means hydrogen-based DRI. And it will go for the electric arc furnace for melting to produce the liquid steel. But another is this hydrogen-based DRI. It can go for the combination of smelter as well as the DF route. You can again produce the liquid steel. And hydrogen-based DRI, it is very finer in nature. Like if you produce in fluidized bed reactor, then this FBR means hydrogen-based fluidized bed reduction reduced DRI, electric arc furnace route also it can produce the liquid steel. And finally, which process is I'm going to discuss is like hydrogen plasma smelting reduction. Here, the iron ore in the form of fines, obviously, or iron-rich waste material, you can directly go for the hydrogen plasma smelting route so that you can directly produce the liquid steel. So if you uh, compare these four different route, hydrogen-based route, so first three is hydrogen-based DRI process production. Then this hydrogen-based DRI production and EAF route combination, what happens? It needs the cleaner iron ore. Why? Because lean grade iron ore contains a lot of gangue materials which cannot be treated in electric arc furnace efficiently. Energy cost will be very high. Therefore, the beneficiation is required. Like if you want to produce the DRI, you have to go for the pellet route. Means the mineral after mineral beneficiation, you have to produce the DRI grade pellets, and then these pellets will be reduced and melted in electric arc furnace. But this high hydrogen plasma based smelting reduction, you can treat low grade or high grade or iron bearing waste materials like iron ore slime or iron ore fines, etc. Because here the input materials is in the form of fines. Okay, so fundamentals is like here high energy hydrogen plasma is used to reduce the iron ore, as the hydrogen plasma having higher melting temperature, a higher temperature, therefore at that condition reduced as well as melt. And it can operate also with the pre-reduced materials. Okay, and it is applicable for reduction of various ores and other waste materials. Okay, which is the byproducts is iron bearing materials waste which is generated in the integrated steel plant you can use. So, but this process should be developed and scaled at commercial process so that it can be a part of a non-conventional route of steel making. So here, this picture is indigenously fabricated transferred arc plasma furnace. This setup in NIT Durgapur, we do this experiment, different smelting operation experiments we have done here by this furnace. We have recovered multimetallic components from the waste materials, thermal power plant waste materials like fly ash, bottom ash by the smelting reduction under this plasma environment. We have recovered the aluminium from the waste material by this melting reduction route by this plasma. We have prepared the crude stainless steel from the chromite ore fines to make the iron, chromium, nickel, nitrogen alloy, where the nitrogen can replace the somehow nickel. Therefore, directly you can get the uh, stainless steel, austenitic stainless steel, nitrogen bearing stainless steel. If you use the nitrogen plasma, okay. We have also do some experiment, not on in plasma, but this furnace as a arc furnace to remove the different impurities by using high flux DRI in this electric arc furnace. So the present topic which I am going to show you, this is based on this paper, like the removal of carbon, silicon, manganese, sulfur, and phosphorus in iron made under hydrogen plasma. This is the new concept, like in DRI process, if you see the in iron making process, a lot of slag is generated. If you see the source of this slag generation, so if you see the iron making area, iron making slag, primary steel making as well as secondary steel making are the steel making slag. And this steel making slag is actually it is for removing the impurities. For removing the impurities, what happens in normal BOA process? Impurities is oxidized. To capture this, to eliminate this, it requires the lime. Therefore, this lime is actually mixed with this acidic oxide like silica, um, then it forms the slag. So this slag, and can you replace this slag in conventional iron making impurities removal process? This slag will generate. So we have taken some initiative to um, remove the impurities in a different way by the hydrogen plasma. Then if you see the major impurities removal is carbon, silicon, phosphorus, sulfur, and manganese. You can see the carbon can easily react with the hydrogen as at lower temperature also. Silicon also can reduce with the hydrogen at a temperature which is the steel making temperature, easily can react. Similarly, phosphorus and manganese can also react to form the hydrides, but sulfur having some difficulties. Sulfur, when dissolved in the metal, it will not react easily. Okay. So therefore, the conventional steel making, which just I have discussed, a lot of slag is generated. Then this slag is handling and disposal is a problem, and a highly alkalinity nature of this slag, it restricts the use of landfilling or making the road, etc. So if you can produce the steel with a sustainable metal, sustainable manner, then the normal conventional steel making like oxidizing followed by the reducing is a two-step process, as well as it removes the, it takes the time. So, and it generates the slag. Therefore, if this steel can be produced like in a shorter duration, it means if we can remove the impurities in a single operation, then obviously the time consumption will be less. Okay, time requirement will be less. And if we can produce some product which will not form the slag, okay, suppose in the form of any dust particles, okay, or metallic hydride forms, so then you can avoid the slag generation. It means you can, if you can do the slag steel making in a single stage, it will save your time. And if you can minimize or escape the slag generation, or then it will be a still sustainable steel making process. Okay, so how we can do it? So as we discussed, the hydrogen can reduce the all impurities at a temperature near about within the temperature of the steel making. But the problem of hydrogen is, like if you see the reaction hydrogen with the sulfur dissolved in the iron. So due to the positive gives free energy, the desulfurization of the molten iron with molecular hydrogen, it is difficult. Okay. Therefore, to make it possible, what can we do? If you see this equation, the sulfur dissolve in the liquid metal, if it the form of hydrogen ions, so what will happen? You can see minimum temperature which is required for this feasible reaction is near about 2500 Kelvin. It means if you can increase the temperature at a certain level, then the hydrogen in the molecular state, ionic state, when it will go, so it can uh, react with the dissolved hydrogen. Okay, from this mm, actually this area actually motivated us to do this work. Like hydrogen plasma, is it feasible to remove the sulfur? If it is feasible to remove the sulfur, what will happen? We can remove all the impurities in a single state, because hydrogen can react with all impurities present. So this is the why we need hydrogen plasma for refining of the steel, because fact stage analysis it shows near about 2500, more than 2500 is required. Then why we have chosen the plasma? Because plasma, it generates the more temperature. Okay, and we have chosen the direct transfer dark plasma, because the transfer dark plasma, the heat generation, heat utilization is very high, because the transfer dark plasma, the arc is directly exposed to the liquid metal surface. Okay, therefore, in a non-transferred plasma, which is the heat utilization is less than 50%. But in case of transferred dark plasma, the heat generation, heat utilization is more than 70%. It means if you want to produce more heat, then obviously you have to go for this transferred arc plasma, because here the arc is directly exposed to the start to the metal upper surface of the metal. Okay, therefore we have chosen this arc plasma, transferred arc plasma parts. We have for taking the raw materials like high impurities present pig iron we have collected, high impurities present to see the removal pattern of the different impurities. Like normal pig iron, if you take, it will contain some 0.04%, 0.03% sulfur. Therefore, the removal kinetics is very difficult to observe. Therefore, we have collected some pig iron which contains high amount of sulfur, high amount of silicon uh, and carbon also. Generally, this type of pig iron is collected from the newly relined blast furnace. What happens? Newly relined blast furnace having the cold hot temperature is less, and coke input is very high initially. Therefore, the carbon, silicon, as well as sulfur content in this liquid pig iron generally is very high. So different raw materials along with the mild steel rod, hoop iron, it is the very pure iron, pure form of iron, less impurities we have used. These are the combination which I have discussed. You can see the sulfur content is 0.074. Silicon content is very high, 4.10. Simultaneously, near about 3% is the carbon. Okay. Therefore, this raw materials we have collected, and to see the different system, what is the effect of manganese present to desulfurization, and what is the effect of carbon present in the desulfurization. We have prepared different system. Like for hoop iron, it is the pure system, so that we can produce this one. Then for generating, producing the FES system, hoop iron as it is the purer form, then it is melted in presence of the iron sulfide to make the FES system. And to make the FeMnS system, ferromanganese as well as the FES and iron, hoop iron is used. Similarly, we have prepared the FeSIS, FeCS systems. This is the actually experimental setup. You can see here the dust collection system here, and this from this rod, hollow rod, graphite electrode, we introduce the hydrogen. 13 number, you can see the gas input here. Okay, this is the tilting arrangement, and this is the closed chamber. So for gas collection, we used one water-cooled jacket where the gas is passed through this jacket, and when it turns, direction is changed, the solid particles is settled down here. Okay, and from the gas outlet, we suck this gas from the bladder, and it we send it for the analysis. This is the gas cleaning setup, because hydrogen along with the argon we used, therefore some cleaning is required to avoid the explosion. You can see here, after melting, up to the melting experiment, we use the normal arc, because hollow electrode during the conventional melting, it may jam the holes. Therefore, after melting, when liquid metal is prepared, then we transfer it to the hydrogen plasma. Okay, by replacing the electrodes from solid to hollow electrode. Then we have taken some point samples. You can see point samples by taking this crucible copper mold, and we analyze it. Okay, and the furnace was operated at arc constant arc current 232 to 265 amperes, and 12 kVA power rating we maintain as per the arc stability from the previous experiment. We have fixed it. Then this input gas, you can see this electrode is directly exposed. It means that when the gas, hydrogen gas will be in front of the arcing zone, it will dissociate and it will form the plasma, and it will directly expose to the top surface of the liquid metal. These are the kinetic study of impurities removal. You can see the carbon removal is very faster. Okay, within 5 minutes, you can see a lot of carbon will remove. Okay, so but what we have seen is sulfur is slightly delayed. After that, drastically it decreases. This slightly delay is actually, I will discuss details in the conclusion area. So this slightly delayed is due to as carbon is a major portion here. So then this carbon, as the carbon removal is very faster, and the temperature generation is also required here, because after 2500 Kelvin, then effectively sulfur will remove. Therefore, initially the sulfur removal is slightly delayed. After that, you can see when the exposure time gradually increases, as the liquid metal surface is also superheated and the major impurities like the carbon is removed, then the removal of the sulfur is happened, because sulfur is surface active element. When the surface the impurities at the surface will remove, then the sulfur will try to come at the upper surface as a surface active element. Therefore, you can see that drastically the sulfur will remove. The silicon pattern is somehow slightly initially slightly decreased, after that it increases. But the two factors, two other impurities like manganese and phosphorus, we observe very less removal. Actually, what we observe when the kinetic study is done, at a regular interval, we taken out the sample in every time as this surface is exposed to the atmosphere, some oxygen is reacted with this manganese or silicon to make the thin layer of silicon oxide or manganese oxide. Then this thin layer actually restrict the further reaction of this sulfur hydrogen with the upper surface. Therefore, it creates this removal of these two elements specially. These are the degree of removal of different elements for different hydrogen exposed content flow rate like 0.5 liter per minute, 1 liter per minute, 2 liter per minute. Sorry, this one is 1 liter and 1.1 liter. This is 2 liter and 2.2 liter and 4 liter. What we observe is like when we increase the hydrogen content up to the 2 liter per minute hydrogen, the removal is increases. After that, it decreases. But when we give the 2 liter hydrogen and 2 liter argon, the arc instability it observes. It means the hydrogen or argon combination is so high that it will interrupt the RP proper arcing. We observe in case of 1 liter plus 1 liter argon combination, we got the optimum removal rate. Okay. But if you see 2 liter hydrogen, although the arc is unstable, but you can see the 90%, more than 90% is hydrogen is removed. It means the for removal of the carbon, hydrogen, only hydrogen gas is enough to reduce the carbon. But plasma is required to reduce the sulfur, which is observed in that sulfur removal cases. Okay. So it means the sulfur, you can see here, the sulfur removal is optimum in case of 1 liter hydrogen plus 1 liter argon combination. Actually, argon, what is the requirement? It actually stabilize the arc. Okay. When you increase the hydrogen content, obviously the reaction will increase, but arc instability will also occur. But if you give some stabilized gas like the argon, what will happen? The arc will be stabilized. Continuous arc will be there. And to maintain the high temperature for the effective desulfurization, what is the requirement? Prerequisite is it arc should be a smoother arc. Continuous arc is required. Otherwise, if the temperature is fluctuating or continuously at the top surface, the sulfur removal will vary. So from this study, as I have discussed, up to 99% carbon, 81% sulfur, and 76% silicon, and 41% manganese, and 30% of phosphorus was removed after 70 minutes of exposure time as a 1 liter hydrogen and 1 liter argon gas combination. Okay. So I think, sir, I have 10 minutes or more time, na?
Yes, yes, you can continue for another 10 minutes.
Okay. So actually, for establishing this impurities removal process, we do the regression analysis as well as the ANN-based predictive modeling. Because ANN modeling is why it is required, because as the input as well as the output both are changing. In normal regression analysis, what you can establish is like reaction time and gas flow rate. You can make some formula so that for a particular, like carbon removal, what is the effect of reaction time and gas flow rate? For silicon removal, what is the effect of reaction time and gas flow rate? But as this impurities removal process is continuously removing this, simultaneously removing the sulfur, carbon, silicon, manganese, phosphorus, then only this regression analysis, it cannot predict actually the effect of both inputs to the outputs. So here, initially we dynamic Taguchi and multi-regression analysis was done by taking two input parameters, reaction times and the flow rate. Actually, third one parameters we should also consider like the temperature. But in our system, what was the drawback is we should not vary this temperature, because this at the plasma zone at the when the temperature is increased, we cannot vary in 2100 degrees centigrade or 2400 degrees centigrade or 2700 degrees centigrade. If we can vary, then this process will be better. We can get another variables input like A, B, C will be the temperature. Here, we have taken three flow rates, 0.5 liter, 1 liter, 2 liter, and time 0, 40, and 70 minutes as level 1, level 2, level 3. And from the regression analysis, if you see both the reaction time and flow rate are significant factors because the confidence level is 5% confidence level. You can see both are the significant parameters. So here the good fit model was observed as considering the R square and R square adjacent values. This is for the carbon. And in case of sulfur, reaction time is significant at 10% confidence level, and flow rate is significant at 5% confidence level. It means flow rate is a factor here more as compared to the reaction time. But what happens if you increase the reaction time for a prolonged time? What will happen? The temperature of the top surface will increase, and it will again further desulfurization will increase. If you see the contribution of the flow rate in reducing sulfur is better than the reaction time. Therefore, the increasing the reaction time also demands for an increase in flow rate, because the best removal of sulfur is possible at an optimal temperature band, which I have discussed. The minimum temperature is required so that the desulfurization will be taking place. Otherwise, sulfur will not react with the hydrogen. In case of silicon, although both flow rates and reaction times are significant factors, but the flow rate is more impactful than the reaction time. The best result is observed in the middle level of flow rate, like 1 liter per minute in case of silicon. In case of manganese, both factors are non-significant, as I have discussed, like the formation of a very thin slag layer, okay, which actually retards the further reaction of this hydrogen with the manganese. Therefore, here when we go for this analysis, then we can see that both factors are non-significant in nature. But comparatively, if you see the reaction time has a greater role as compared to the flow rate here. In case of phosphorus, if you see both factors are not significant, possibly reason I have already discussed in case of phosphorus also. So one top layer was produced a very thin slag layer. Okay, so therefore these are the reason for this. But comparatively, if you see the reaction time has a greater role as compared to the flow rate here. Then we go for the neural network based predictive modeling as the input and output as output parameters is gradually continuously changing. Therefore, we cannot predict in normal regression analysis. Here, the reaction time and gas flow rate are the input, and carbon, silicon, sulfur, phosphorus, and manganese as the output. We have taken 897 data sets, 2 inputs and outputs. Training and validation and test was randomly divided into 70 is to 15 is to 15. Initial weights are randomly generated from this equation, and training algorithm we have taken LM method, and maximum epochs we have taken under consideration 1000. and one hidden layer, numbers of the neuron varied from 3 to 10, and we got the best result in the hidden neurons 9. You can see here 2.48 into 10 to the power minus 10 is equal to that any performance is best performance in case of the hidden neurons 9. And here the error histogram, you can see almost perfectly matching. And this is the best validation performance in epochs 1000. This is the error histograms. From this multi-regression analysis model, we can conclude that already the conclusion from the experimental data, it is validated. Like upper level for the both inputs, like the reaction times and flow rates, provides the best result. But higher the magnitude of the factor, the better percentage of the reduction in case of carbon, sulfur, silicon, phosphorus, and manganese. When we keep the flow rate constant and increase the reaction time, it gives the better result. When the peak reaction time is kept constant and flow rate is varied, the middle level, like 1 liter per minute flow rate, it gives the optimum result. Both these two observations we have already observed in the fundamentals findings of our experimental work. The contribution of the flow rate is reducing sulfur is better than the reaction time. Therefore, increase in reaction time also demands an increase in flow rate, because the best removal of the sulfur, it is possible at a optimal temperature band, which is the minimum temperature range which is required for the desulfurization. Although the flow rate and reaction times are significant factors for the silicon removal, but the flow rate is more impactful. Then the best result observed in the middle level of the flow rate, like 1 liter per minute. Both factors are non-significant for the phosphorus or manganese. It may be due to the non-consideration of some important factors during the experiment, like the temperature one factor, it may be the one factor, another is the avoidance of the slag layer formation above the melt, which will it affects this removal of impurities. Thank you for your presence.
Okay, thank you, sir, for this wonderful talk. Now the house is open for question and answer. Any questions? Yes. Sheikh Wasim, you want to ask some question?
Yes, good evening, sir.
Good evening.
Just wanted to understand the power consumption requirement for hydrogen plasma-based technology, smelting reduction, versus the three-stage reduction. How do you see that comparison, the usage of power consumption?
This is related to our experiment, which I have discussed, or general?
In general, I'm asking. Once this experiment will be industrialized or in use, in case everything goes through, so in that case, the comparison between single-stage reduction to a three-stage.
So in case of this plasma, if you see the plasma, as it generates very high temperature, so it will be beneficial for means the lower energy consumption you can generate the means high temperature, number one. Number two is like as we discuss, this is not for this impurities removal, which we discuss in case of the high plasma based melting reduction process, where the smelting for smelting reduction, as this direct solid particles to iron making, therefore you can skip a lot of intermediate step like burden preparation, agglomerations, beneficiations, iron making, and finally the steel making. Then if you can cut down this intermediate step, and if you calculate the total energy consumption, it will be less as compared to the conventional. But scaling up to a commercial stage, it requires.
Thank you. Just a follow-up question on your experiment. You told
Yes.
that 1 liter per minute consumption of argon and hydrogen is the optimum, which will give you optimum results. What was the amount of raw material which was used in this experiment? The amount of pig iron and the scrap utilization. Could you just?
4 kg. Acha, 1 minute. So I can show you. Actually, our capacity is 4 kg capacity. We cannot take more than 4 kg. I am sharing again. Is it visible, sir?
Yes, it's visible.
Is it visible? Huh?
Yeah.
You can see here our pig iron is 4 kg because our capacity is 4 kg. Therefore, the pig iron content we have taken as a 4 kg. But if we go for the smelting reduction route, where the slag will generate, then our capacity enhancement is required. Like crucible size enhancement is required because some free boat area is required so that we can accommodate the viscous slag. That condition, we generally take 2 kg liquid metal and we kept the remaining portion as a free boat area for accommodating the slag, extra viscous slag.
Thank you.
And now we are trying to enhance the capacity because for kinetic study, it requires so much liquid metal. Therefore, if we go for the smelting reduction and it generates the slag, therefore the capacities will be high. Like capacity should be minimum 7 to 8 kg or 10 kg capacity furnace, so that we can produce 4 kg liquid metal, 5 kg liquid metal, and remaining portion we can kept as the freeboard area for slag handling of the slag, viscous slag.
Okay, any other question? Okay, sir, I want to ask one question.
Yes, yes.
If you replace argon by mixture of argon and helium,
Yes.
because of the advantage of work function of helium, can
Yeah.
we get more stability?
More stability because helium is more stabilizer. Stabilizing point of view, if you see helium is more arc stabilizer as compared to the argon. So argon is actually readily available here, cheaper in nature. Therefore, we used it, but we can use helium also. What will happen? We can introduce more amount of hydrogen, like 2 liter plus 2 liter combination. What happens? The arc instability we cannot ignore, but it may happen like 2 liter hydrogen and 1 liter helium. It may do the better result because as the stability point of view, helium is better. Therefore, with less amount of helium, we can stabilize the arc more. Therefore, we can introduce hydrogen. Therefore, the time consumption will be less.
Okay, one more question. Now, when we
Yes.
create a arc over a liquid molten material, so iron also get reacted with hydrogen, and it will form iron hydride.
Iron hydride, yes.
So there is loss of material.
Yes. We as I have shown you this 1 minute. This jacket, is it visible, na?
Yes, yes.
This jacket actually intentionally we kept this. This is the cooling jacket. Why it is required? Because metal vapors will form at that high temperature. Okay, metal vapors in the form of iron hydride, silicon hydride, manganese hydride. Majorly we observe. Achha, I have not shown you the XRD analysis of these dust particles. Sorry for that. Actually, due to the time constraint, I skipped that. So we got the metal hydride, mainly the iron hydride, manganese hydride. Silicon hydride we have not got because actually silicon hydride at that temperature when it goes to the upper portion, it again revert back to the silica. Therefore, we have got the silica, but manganese hydride, iron hydride, and different types of complex hydride we have observed. Where? Because it is actually, if it is visible, You can see this my cursor, na? This water jacket area, when we open this water jacket area, major deposition is formed for the metal hydrides. And from this area, gas, where the dust catcher is there, which is for the dust capturing area, we got majorly the solid particles. Okay, but major hydrides, it is deposited here at the colder zone where the water circulation is done.
Right. And one more question then, how deep the effect of that plasma will be there in the molten material? It will concentrate only on the surface and it will remove only the impurities on the surface. How deep it can
Nay, actually, plasma some impingement velocity is there. Like arc is not very lower impingement velocity. Arc having some impingement velocity. Therefore, what happens? Some ions, it goes, hydrogen plasma, it goes inside also. But the majorly, the hydrogen is reacted at the surface of this liquid metal. But due to the impingement velocity of the arc, or it is called the arc pressure, with this arc pressure, some amount of plasma, hydrogen plasma, goes into the solution also.
But how deep? And beyond that, what happened?
Actually, you cannot measure this at high temperature. We can calculate this due to the liquid metal density, and if you calculate the velocity of the gas, then we can calculate the impingement velocity or the profile which is created, like the crater which create, diameter of the crater which create. We can measure it.
And do you use stirrer in the molten material?
No. There is no provision for stirring.
Okay. Any more questions from the audience? Okay. If not, then we'll close this session now. We thank you, Professor Arup Kumar, for this wonderful talk and for accepting our invitation and delivering.
Thank you from my side also, Ganesh ji, Wangsuman ji, as Dinda ji. Okay, for inviting me to deliver the lecture in your 5 days workshop. Thank you all.
Okay, thank you. Okay, sir.
Thank you, Professor Mandal. So, thank you.
Okay, so this is the end of the day. Now I request all the participants to join tomorrow. Tomorrow session will start